everyone, this is video 1.1.1. That means it's Unit 1, Lesson 1, Part 1. So we're going to start off today by sketching particulate diagrams of each of these following substances here. This should be a review of what you learned in your first chemistry class, but if not, don't worry, just stay tuned. Okay, the first one, carbon dioxide gas at STP. STP, as you'll recall, means standard temperature and pressure. So in our case here, our standard temperature is going to be 0 degrees Celsius, and our pressure is going to be 760 torr. And that's the same as 1 atmosphere. 760 torr, or 1 atmosphere, those are equivalent. And you can find all of your equivalent pressures on the back of your periodic table. So at this point, I'd like you to pause this video, grab a piece of scratch paper, and sketch out what you think CO2 gas looks like at this temperature and this pressure, standard temperature and pressure. Okay, so this is hopefully close to something that you got. Now there's lots of different ways to show sketches of particulate diagrams, but this is just one. So each of my little spheres here shows CO2, a single CO2 molecule. And these little tails show that it is moving. So this is far apart. So these molecules are spaced very far apart because they're a gas. They're not very dense. And these tails are showing that the CO2 molecules are in constant motion, because as we know, any gas is always in motion. So for our explanation, we're going to say that CO2 is a gas. So the molecules are far apart and are in constant motion. And that motion is shown by tails. So just go ahead and sketch this out. Sketch out just a quick sketch. You don't need to draw this many. Just draw 3 or 4. Okay, next up, tin oxide. This is a solid. So we can tell that this is going to be ionic. And we can tell that because tin is a metal and oxygen is a nonmetal. So this is important. This is going to help you all year. Any metal plus a nonmetal, that's going to be an ionic compound. So made of ions that are attracting each other. Up here, for our example for CO2, we had carbon and oxygen. Both are nonmetals, so we can tell that that is going to be a covalent compound. Okay, so back to tin oxide. I want you to go ahead and pause the video and sketch out what you think tin oxide looks like. Okay, we're back. So this is my representation of tin oxide. So you'll notice here that I've actually separated the ions and I've drawn both ions. So tin takes on a 4+ charge, oxygen 2- charge, and you'll notice that these ions repeat. So this is an ionic solid, and this whole structure here would be called a lattice. And that lattice is made of alternating positive charge and negative charge. So you see you have negative, positive, negative, positive, negative, positive, negative, and then there's a negative touching the positive. You don't ever draw 2 negatives touching because they repel, likes repel, and you never draw 2 positives touching because those also repel. So again, we have positive, negative. The positive ions we call cations. A fun way to remember that is cats have paws, so it's a positive ion. And an anion, a negative ion. An anion is a negative ion. Okay, so for our explanation, we are going to mention that tin oxide is an ionic solid. And it's going to be made of a lattice of alternating tin 4+ cations and O2 minus anions in a 1:2 ratio. And we got that ratio, so for every one tin, there are going to be 2 oxygens. And that's because tin has a 4+ charge, and each oxygen has a 2- charge. Now, don't get confused. Don't think the 2- charge came from here. This subscript tells you just how many oxygens are in the molecule. So we have 2 2- charges, which makes a total of 4-, and we have 1 4+. So that's why we get the 1:2 ratio. Okay, next up, 0.2 molar calcium hydroxide. And this little AQ here, this means aqueous. So aqueous just means that whatever this molecule is dissolved in water. Aqueous is always dissolved in water, like aqua. So this M is molar, that's just a concentration, so your concentration of moles per liter. You should recall that from your previous chemistry class. So I want you to go ahead and pause the video and draw what you think this dissolved calcium hydroxide looks like in water. Okay, we're back. Here's what I have. Now, you don't have to draw all these water molecules in the background. That's just the solvent. I just wanted to show you that these are dissolved in water. What I really want you to draw is the separated calcium and hydroxide anions. Now, I keep saying hydroxide, this OH minus. That hydroxide is a polyatomic ion. There are several of those that you'll have to memorize for this class, and several that I'm sure you memorized before for your other chemistry class. But this is hydroxide. It's a polyatomic ion. It's got a special name, OH minus. Calcium 2+, it's a calcium anion, or sorry, cation there. Cation is positive. Okay, so why did this separate completely? You might be thinking metal, nonmetal, but the reason that this is completely separated is because it's a strong base. And you'll recognize that this is a strong base because in this class you're going to need to memorize a list of strong acids and strong bases, and it's going to help you for the whole year and on the AP test. There aren't very many, so you need to memorize the strong ones. And strong acids and strong bases both ionize or break apart 100%. So that means they come apart 100% in water. So for our reasoning here for why this looks this way, this particulate diagram is calcium hydroxide is a strong base. So it ionizes or breaks apart 100%. So there are calcium 2+ ions and hydroxide ions in a 1:2 ratio. Surrounded by water. And again, we know that that ratio is from 1 calcium and 2 hydroxides. And we know it's surrounded by water because this is aqueous, and that's what aqueous means. That's the definition. Okay, SO2, sulfur dioxide gas. Now, this is at 30 degrees Celsius and 400 torr. So going back up, we're really going to be comparing this with our first gas. First we had carbon dioxide gas at STP. That temperature was 0 degrees Celsius, and that pressure was 760 torr, or 1 atmosphere. Here we have 30 degrees Celsius, which is a higher temperature than our STP, and 400 torr, which is a lower pressure than our STP pressure. So I want you to go ahead and pause it. And again, you're just going to be drawing spheres. This is a covalent compound, so nonmetal, nonmetal. You don't need to show them breaking up. They don't break up. They stay whole because this is a covalent compound. It's not being dissolved in any way. We're just trying to show what the molecules looks like. So go ahead and pause this and draw that. Okay, we're back. So this is similar to what you should draw. So let me point out the differences here. The size is pretty similar, so you don't really need to show that. What I want to show you here is that at 30 degrees Celsius, these molecules are going to be moving faster. So in reality, I should elongate these tails. So I want you to draw them with slightly longer tails because they're moving just a little bit faster than they were at 0 degrees Celsius because they are warmer. Okay, next, 400 torr. This is a lower pressure. So when gases are at a much lower pressure, they can spread apart more. And so these gases are at a much lower pressure, so these molecules are spread apart just a bit more than the ones at 760 torr. So for our explanation, we're going to say SO2 is also a gas. The sample in this case is roughly half the pressure. This is almost 800 torr, so we'll say the sample is roughly half the pressure. Of the CO2 sample, and it is at a higher temperature. So the molecules are more spread out and they're moving faster. Okay, so we're going to go ahead and rank these four substances, these four samples, in order of increasing density. So we want the least dense sample here and the most dense sample here. So go ahead and pause this and predict what you think should go on each line, which substance. Okay, so your least dense sample you should have said would be SO2. Your SO2 is the least dense. There are fewer molecules in this area, so SO2 gas, followed by our next gas. So the only other gas in this case was our CO2 gas. And then liquids and aqueous substances, they are the next most dense. So we're going to write our 0.2 molar, 2O molar calcium hydroxide. And then finally our solid is the most dense here, so SnO2. That's our solid. I forgot to write my state. This is AQ for aqueous. Oh, I'm sorry, couldn't see that. Okay, so this is our order of increasing density. So why? Gases are the least dense. This one is the least dense. It's less dense than SO2 for those reasons we talked about. Higher temperature, lower pressure, allowing them to move faster and spread out more. So gas is least dense. Followed by aqueous substances, or in this case we don't have a pure liquid, but if we did that would be here as well, and solids. The SO2 is less dense than the CO2 gas due to the lower pressure and higher temperature. Okay, that is it for our first video, 1.1.1. So go ahead and jot down any questions that you have. And that's it. Thanks for sticking around.